You may have noticed in the definition section that there were several definitions for price. There's the price that is simply the selling price per item. Then there's a supply function and a demand function. These were defined as the price was the supply function and the price as the demand function. These are functions where the price is defined on how many items I'm willing to either consume or supply based on the price. When we look at this, it's important to notice that if I am determining the price based on supply, I will see that as supply increases, the price is going to increase. In other words, the more people are willing to pay, the more I'm willing to make. In terms of demand, this is the price at which consumers are willing to buy the item. So demand is going to increase as that price decreases. We're going to look at some more examples here in a minute, but it's important to note that there is what we call a price equilibrium. And that's where the supply function equals the demand function. That means that the prices match to a point that it's enough of a price that consumers, or a low enough price consumers are willing to buy it, and a high enough price that suppliers are willing to create it. So let's look at some examples here. First of all, let's consider something about car rental. Suppose we have the total cost of renting a car looks at a fixed cost, which is $35 a day, no matter how far you drive it, and a variable cost of 15 cents per mile. We need to be able to write a function for this. If you remember from our discussion in functions, we know that that cost function is going to be a sum of the variable costs plus the fixed costs. In this case, we're defining the amount we drive based on X. And we know that that variable cost is going to be 15 cents per mile plus the fixed cost, which in this case is $35. Notice that if we don't drive at all, so C of 0, that value is going to be 35. If I rent the car and it just sits in my driveway, I'm still going to pay $35. However, I can also determine for part B, the cost for driving 500 miles in a day, which is going to be the 0.15 times 500 plus 35. It will cost me $110 to drive it 500 miles in that day. Let's look at an example where we're using the revenue terms based on our definitions previously. If we have a manufacturer that determines that the revenue that is generated by selling X units is a linear function, and that's key there to remember that we know linear is of the form y equals mx plus b, and we know the revenue from 20 units is $380, and the revenue from 15 units is $285. We want to find the revenue function. Since we know it's linear, these values can be represented by ordered pairs. 20 units results in a revenue of $380, and 15 units results in a revenue of $285. And remember, since it's linear, that revenue function is going to be some mx plus b, and we can use our steps for finding the equation of a line. We find the slope first by doing change in y, which is going to be 380 minus 285 over change in x, which is going to be 20 minus 15. This gives us 95 over 5, or a slope of 19. So now we know that the revenue is equal to 19x plus b. And then in order to find our y-intercept, or the amount of revenue when 0 units are sold, we can plug in either of these points. If I plug in 380 for y, I get 19 times 20 plus b. 19 times 20 is also 380. And when I subtract 380 for both sides, notice that my intercept is 0, which makes sense if I don't manufacture X units, it's not going to make me any revenue. So my revenue function is simply 19X. According to that example, if we follow this revenue line, the amount we could make would increase indefinitely. However, we know in the real world that things reach a limit. For example, here, when they're making this value, it can keep going and going, but what happens when things run out or consumers don't want anymore? Well, let's look at another example of revenue, and we'll talk about this a little bit more. This one's a little more complex. Suppose that we have a belt company that determines the cost here of manufacturing belts is $2 per belt. So our cost has a variable part of 2 per belt plus 300 in fixed costs. Their revenue, however, they sell them for $3 each. So their revenue is solely based on the amount that they sell the belts for and the amount they sell, which in this case is 3X. What we want to know is, when do they break even? When does the cost meet the amount they're making? Because notice they are selling the belts for more than it costs to make each one. We need to figure out when the cost equals the revenue. Setting these equations equal to each other, we can combine like terms. I subtract 2X from both sides, and they are going to break even when X is 300. If we look at these equations here, notice that we are plotting the revenue at 3X, and we are plotting the cost. Even if we make no belts, the cost is still $300, and the break-even point is right here when they make 300 belts. However, notice that this would show that that revenue is going to keep going up. But we know that at some point we run out of people to buy belts, or perhaps we can only make a certain number of belts a day in our company. So in other words, we have to have a model that more accurately depicts this situation. At some point, revenue is going to start to decline again, which may be more indicative of perhaps a quadratic function. Let's look at an example here where we have a company that determines the cost is 500 plus 140X, and that the price they should charge is this. Well, working through these 4 parts, we can find the cost function. Well, they've given us the cost function. The cost function is 500 plus 140X. The revenue function is going to be the amount we charge times the number of things we sell, the amount you make per belt. Well, we know, or in this case, whatever they're making, we know that the price is 200 times X times the number that we sell. When we multiply this out, notice that we get a quadratic. That's our revenue function. The profit that we make is going to be revenue minus how much it costs. So we can do revenue, which is 200 minus X squared, minus the cost, how much we have to spend to generate our product, and combining like terms, and I forgot my X here, we get 200X minus X squared minus 500 minus 140X, which leaves us with negative X squared plus 60X minus 500. Again, it's a quadratic. To find the break-even point, that's where revenue equals cost, or where the profit is 0. So I want to know, where does this equal 0? This is where your quadratics skills are going to have to come in handy to solve. I'm going to get rid of this negative and rewrite this as X squared minus 60X plus 500. And when I factor, I get X minus 10 times X minus 50, which tells me that when I make 10 of the product, or when I make 50, I will break even. Looking at this graphically, you can see that there's 2 break-even points, and our profit is anywhere in between those values. When I make 50, I'm going to go back to making no profit. When I go make just 10, I'm going to make no profit. Somewhere in between 10.50 is the sweet spot where we can maximize profit.